In this next question, we have the section B type of questions. So section B is no longer relevant in the current 2022 syllabus, but then I will just go through whatever questions that are still relevant to the current syllabus. For instance, in this question 8, we are talking about proteins, and protein chemistry is still around. So is the chemistry of amino acids, and so is the polymerization chemistry. What is the type of chemical reaction? The type of chemical reaction to form this polymer chain. We talk about amino acids that can undergo condensation in order to give you condensation polymer called proteins. So you get proteins because you have polypeptide. Polypeptide basically means many peptide bond. So peptide bond is this amide bond actually, because we get it from amino acids that have a special name called peptide bond. But then if it is just a normal amide, we just call it amide. So what we can say is all peptides are amides, but not all amides are peptides. So be very careful there. So we are not forming are we forming a polymer? Yes, we are forming a polymer, but the type of reaction is called condensation because we are forming a condensation polymer. Now the next thing is these amino acids are given as the structure here, serine and valine. So what we know is H2N, and then C, and then H and CO2H and R group. This is the general structure of an amino acid. So in serine, this CH2OH is your R group. In valine, this CH3CH is your R group. Now you want to draw dipeptide. You want to draw the val and then the SIR. So if I have the val on the left and the SIR on the right, and what is important is they want the skeletal. If they want the skeletal, I cannot draw any other thing apart from the skeletal. So what I do is, I start by drawing the val. So the NH2 wouldn't react, it's the CO2H that react, for instance. So here, I will lose the OH. I will lose the OH in my condensation. Lose the OH, and then the NH2 here will lose the H from the serine because the serine is on the other side. So I'm forming this new bond in pink. This is NH. NH, in fact, I don't want to show the bond there, it's just NH. And then I just complete the other part of the serine molecule. This is the new amide bond that I'm forming because I break this bond there, C single bond O. I break the NH covalent bond as well. And then I'll form a small molecule, minus H2O, condensation reaction. As I form one amide bond, I kick out one water. And this is part of the val first, and then the SIR, even though they have put the serine on the left side, but this structure they want is val on the left, and then serine on the right. So there's val, and then serine, val SIR. Okay. Now this next question is no longer relevant. This is actually part of biochemistry, but you can think about in the context of intermolecular forces, obviously. So different types of amino acids, maybe I should talk about it. Different types of amino acids have different R group. I just talked about the structure of amino acids earlier, where you have the basic amino group, the acidic carboxylic group, a hydrogen, and an R group. Depending on what R is, it will affect the properties of the protein chains. Different types of amino acids have different R groups. And these different R groups, they can form different interactions with each other. So different R groups will have different interactions. Different R groups form different interactions with the CO or the NH or other R groups further down the chain, because you have a long chain, right? Further down the polymer chain. So for instance, we're going to specify a couple of things. The best kind of answer would be to specify a few things. So example, between CO, delta minus delta plus, and the NH, you can have hydrogen bond. Hydrogen bond is pretty strong, and that is usually what is holding part of the really strong intermolecular forces that holds protein together. What else can you have? You can have between the non-polar hydrophobic Hydrophobic means they don't dissolve in water because they're non-polar. Alkyl chain. So what you get is you just get the London dispersion forces, which is just van der Waals, or London dispersion forces. What else can you have? I guess the hydrogen bond is just a strong version of permanent dipoles, right? You could also have between the SH and the SH residue of cysteine. So the biology student would know what I'm talking about. This is the one that will give you the disulfide bond. It's actually the chemistry of hair straightening. So your hair curls up as they form the disulfide bond. So you get those really foul-smelling chemicals in hair salons, and those things break the disulfide bond, and they will straighten your hair again by breaking your disulfide bond. Anyway, not that much chemistry there, mostly on biochemistry. This next part of the question, so using label diagrams or words, why a particular enzyme may only catalyze a specific reaction or a specific substrate for 2 marks. This is the lock and key mechanism. This thing remained in the syllabus, in the 2022 syllabus. You will find it under rate of reactions. And under rate of reactions, you will learn this as biological catalysis. So enzymes are biological catalysts. So their catalysis is obviously known as biological catalysis or enzyme catalysis. I'm not a big fan of, writing a lot of stuff, I guess. So I'll just write a couple of simple things. So if that is my substrate, let me just pronounce that and write that properly. That's my substrate, so to be metabolized, and this is my enzyme. So what I will get is, I will get an enzyme substrate complex where I just need to move this a bit closer into there. So what I get now is an enzyme substrate complex. And from there, I can then get back my enzyme. I can get back my enzyme and I'll get my products. Does that work? Yep. And then I'll get back my enzyme and I will have, form a different product or something like that. So there will be like products. So we're just drawing simple diagrams to show the idea really. So just to show arrows, because we are representing that going to that. This is your enzyme substrate complex. So why does it only work with specific substrate or specific reaction? So we can say that enzymes have active sites. So these are 3-dimensional pockets, obviously, that only that have specific shape. And this specific shape allowing only substrate of certain sizes, of certain complementary geometry or complementary shape. So complementary means it must match the shape. That's why it's called lock and key mechanism. Complementary shape to fit in and get metabolized or undergo a catalysis reaction or to get catalyzed. So therefore, very, very specific lock and key mechanism there. Now the very last bit here, this is non-competitive inhibition. I'm not going to talk about this. This was actually from the old biochemistry syllabus. In the new 2022 syllabus, in fact, in the 2016 syllabus, it was already scrapped out. You probably learn this in biology rather than in chemistry these days. So, it's a good thing they removed quite a lot of biology from chemistry because biochemistry has never been my strong point. Okay, so that's the end of that whole question there. This question is about DNA fingerprinting. Again, this is part of the syllabus that has been taken out, so we can skip that particular question. The next bit of the questions. So we have these questions that started out with biochemistry, but this bit is still relevant in the 2022 syllabus. In fact, it was relevant to the 2016 syllabus as well. This is under ionic equilibrium now, no longer under a special topic. It's now under an equilibrium as part of equilibrium constant because you have partition coefficient. So when you have partition coefficient, Kpc, so it is equilibrium constant. So that means only temperature can change its value. So it is constant at constant temperature. That's something you need to know. Representing, what does it represent? It is the solubility. Solubility of what? Solubility of a solute in 2, immiscible. Immiscible means do not mix, and these are solvents. So you're trying to extract it into the more soluble phase, and of course you will always have a little bit of it in the solvent in which is less soluble in. Otherwise you will not be talking about equilibrium constant, right? You'll be talking about either full infinity or full zero depending on what is on top. But you don't, you're talking about value, you're talking about equilibrium, because they don't mix. There is a little bit of the solute in each of these two immiscible solvent, and this is constant at constant temperature. So it can only change when temperature, at a constant temperature. I think that is the best definition I can think of, at a constant temperature. That seems more right. So it's a fixed value at a constant temperature. Okay. Now the next bit is really all about calculation. Let me see how many marks there is. There is 2 marks to really run up these questions, but let's think about this, all right? So we have a partition coefficient of this pesticide. Let's just call it X to make our life easy, all right? This is between hexane and water. Because they mention hexane first, it's always been something that I learned from Jim Clark's Chem Guide, as well as from his excellent book on calculations for A-level chemistry. So this one is mentioned first. It will appear on the right side, on the right hand side of your Kpc expression. I'm not talking about equation, I'm talking about expression, in the sense that I will have X in water, and then this is in equilibrium with X in hexane. This is what I meant by, because that is mentioned first, I'll put the X in hexane on the right side, and because it appears on the right side of the expression, maybe I should use equation. Because it appears on the right side of the equation, I will put it on top of my Kpc expression. So what is my Kpc expression? My Kpc expression will be the solubility of X in hexane. So what is the solubility of it in hexane? Divided by the solubility of X in water. Kpc is a value with no unit based on this particular equation there. So I started out with 0.0042 gram of X dissolved in 25 cm of water. So 0.0042 gram, and I don't have anything there, so 0 gram. So this is initial mass. Now what do I have? I have volume of water. Now let's not talk about volume of water first. I then add in some hexane, and then that means some of it will go into the hexane. So if I have equilibrium mass, so some of it will go into the hexane. So I will have X gram. Now X gram is bad. So let's say plus Y gram. So you have Y gram now. 0 plus Y is Y. So this is how much has gone from the water into hexane. If you started with this, but you lost Y gram into the hexane layer, you're going to get 0.0042 minus Y. It's now time for your volume, because we're talking about solubility after all. We can talk about mass solubility, which is gram per volume, mass per volume, or we can be talking about mole per dm cube. We don't know what the pesticide is. It's better we work in gram per cm cube or gram per dm cube. I suppose it's gram per cm cube because the volume here is cm cube there. So the volume in water was 25 cm cube. The volume in hexane was 25 cm cube. So this is volume in cm cube there. So I guess that thing there is in gram and that thing is in gram, so I can cancel out my gram. Alright, now what do I know then? I know my Kpc. This is a lot of space. It's very nice to work with when there's a lot of space. 6.0 for my Kpc. So I have 6.0 equal to solubility in gram per dm cube. In hexane, which is the one on the right hand side of the equation, so Y gram divided by 25, Y divided by 25. At the bottom, I have 0.0042 minus Y over 25. So just do your math and bring up that thing there. So that will become 6.0 times, 6.0 times 0.0042 minus Y, and that is divided by 25. Okay, that's divided by 25 equal to Y over 25. Because you have 25 and 25 at the bottom, what you can do is times 25 both sides, and you will get rid of that 25. We need to expand the bracket very carefully. So 6 times the first portion and 6 times the second portion. So 6.0 times 0.0042, I get 0.0252, and then I get 6.0y is equal to y. So I get 7y equal to 0.0252 gram. Y, which is how much have been extracted. Y is going to be the mass that will be extracted into the hexane is going to be y gram. So let this be y. So my answer really is find what is y. Y is going to be 0.0252 divided by 7. I get a very small value. This is 3.6 times 10 to the minus 3. And this is in gram. Is two significant figure enough? Well, let's have a look at the question. You are given this data, 0.0042, 1 and 2 significant figure. This Kpc, 1 and 2 significant figure. The volume, I guess, 2 significant figure as well. So I guess my final answer to 2 significant figure is totally appropriate given the number of significant figure in the question there. And that's the end of that 2-mark questions and pretty much sum up the whole question, which I skipped pretty much the earlier bit of the question because they were on the the irrelevant biochemistry bit in the new 2022 syllabus.